Section 2.5 is going to deal with quadratic equations. For this section, I'm going to do the notes in two parts just to break it up and keep the individual videos a little bit shorter. So we're first going to look at factoring and solving equations, and we'll also talk about completing the square. So if you recall, a quadratic equation is something in the form ax squared plus bx plus c. And if I'm trying to solve that equation, I need to have it set equal to 0 because of the zero product property, which tells me that if I have quantities or factors a times b all equal to 0, the only way that that is true is when a equals 0 or when b equals 0. And there could be multiple factors. It could be more than two. But the only time that a product of factors will equal 0 is if one or more of those factors equals 0 at that time. Okay, so that's our zero product property. So here I have two examples. The first one on the left, just straight up trinomial factoring. Here my a value in front of the x squared term is 1. So I'm going to go with the sum and product method. So I need two numbers that multiply together to give me my constant term, and are going to sum to give me that middle term, thus the sum and the product. So I need two numbers to multiply to negative 48 and add to positive 13. They are going to be positive 16 and negative 3. So we're going to get x plus 16 times x minus 3, all equal to 0 as our factors. From then the zero product property, I can set each individual factor equal to 0 because now I have it written as a product of factors equal to 0. And when I solve each of these individual factors, I get x equals negative 16 and x equals positive 3. Okay. In example number 2 here, I have 2x times the quantity 2x minus 7 equals negative 12. So right now the left side is written factored, but the problem is this right side is not set equal to 0. So what I'm going to have to do, I'm going to have to distribute, and then I'm going to have to add that 12 back over to the other side so that I have something that is in a form set equal to 0 that I'm actually allowed to try to solve. So if I distribute here, I'm going to have 4x squared minus 14x plus 12 equal to 0. Okay, so one of the things I always tell my kids, especially in Alg 2, is you are always step 0 before you actually start the factoring process. You are looking to see if you have a GCF. In this case, I have a GCF, it's 2. It doesn't quite get rid of all of the coefficients, and really it doesn't make this lead coefficient become a 1 in front of the x squared, but it makes my numbers a little bit easier to work with, a little bit easier to manage. Okay, that 2 essentially can just divide out here because it is simply a constant. If I set 2 equal to 0, I don't get a solution from that. Okay, so what I'm really looking at is this quantity in here. So I'm going to do what's called the A times C method because my lead coefficient is something other than 1. So I'm going to take A, which is the 2, and I'm going to multiply it times C, which is 6. So A, C is going to give me 12. And I want to list out my factors of 12. So I'm going to have 1 and 12, 2, 6, 3, and 4. Because A times C was positive, I'm looking for factors that have the same sign that are going to add then to my middle term, in this case negative 7. So that pair of factors is going to be negative 3 and negative 4. So what I'm going to do is I'm going to rewrite this, splitting this middle term up. So I'm going to have 2x squared minus 3x minus 7x, or sorry, minus 4x plus 6 still equal to 0. Okay, so I'm going to sit here and I'm going to factor a GCF out of that first pair and out of the second pair. So I'm going to have x times 2x minus 3, and I'm going to factor a negative 2 out, so I get 2x minus 3. Had I factored a positive 2 out, I would have had a negative 2x plus 3, and these factors inside my parentheses here wouldn't match. That quantity inside my parentheses, my new GCF, I want to factor it out one more time. So I have 2x minus 3, and what I'm left over is x minus 2. So again, from here now I can set each factor equal to 0. So we're going to end up with 2x minus 3 equal to 0, and x minus 2 equals 0. And we're going to get solutions of x equals positive 3 halves and x equals positive 2. Now, in your head, it's altogether possible that maybe you're sitting here saying, well, 2x squared minus 7x plus 6. I could have factored that, right? The only way to get to 2x squared would have been if I had a 2x and then x in those lead positions. And I agree, 6 also has a small number of factors, 1 and 6, 2 and 3. So I can sit here and try some different combinations and kind of guess and check my way. And if I can figure it out just by brute force that 2x minus 3 times 2 or x minus 2 is going to give me that quadratic, then I didn't have to really do the a times c method. But the problem is, if this term is not a prime number, or if this constant term has a large list of factors, or if both of those things are happening, the brute force trial and error method really starts to become very unmanageable very quickly. Okay, so we want a method, and a times c and then factor by grouping is that other method. Now, you guys might be looking at that and saying, well, that seems really, really familiar. If you remember back, depending who you had for Algebra 2, you may have been shown the box and diamond method. All right, the box and diamond method is the exact same thing as factor by grouping with the a times c, except with a times c and factor by grouping, I'm just not using the graphic organizer of the box or the diamond. I'm just doing it all in the problem. Okay, so let's take a look. Let's do one more with factor by grouping. Okay, so here I've got 8x squared plus 6x minus 9 equals 0. Okay, and this runs into at least the first problem where 8x squared, it's no longer a prime number. So I've got, you know, I could have x times 8x, I could have 2x times 4x, and it's still not a huge list, but it presents more combinations and more problems. So let's do a times c, right? There are no GCFs here. A times c, 8 times negative 9 is going to give me negative 72. So if I list out my factors of negative 72, I'm going to have 1, 72, 2, 36, 3, 24. Let's see, we're going to have 4 and 18, 5, no. We're going to have 6 and 12, and then 8 and 9. So now what I want, right? A times c was negative, so I know my factor pair, one's going to be positive, one's going to be negative. I need a factor pair here where one's positive, one's negative, and the sum is positive 6. What I'm going to get is that negative 6 and positive 12 is going to meet those conditions. So again, I'm going to split this middle term, right? So what I'm going to have then is 8x squared minus 6x plus 12x minus 9 equals 0. And again, I want the GCF of my first two terms, and then I'm going to do GCF of my second two terms. So GCF of the first two terms is going to be 2x, and we left with 4x minus 3. GCF of my second pair is going to be 3, and I'm going to be left with 4x minus 3. Again, what's inside parentheses, if it factors by grouping, should match. That is my new GCF. I'm going to pull it out. So I'm going to have 4x minus 3, and I'm going to be left with 2x plus 3, still equal to 0. At this point now I can set each factor equal to 0. 4x minus 3 equals 0, and 2x plus 3 equals 0. And when I solve my two factors, I'm going to get x equals 3/4 and x equals negative 3 halves as my two answers here. Now, the other thing you might be saying is, does it matter which order I write those two terms when I split that middle term? And the answer here is no. So I want to show you that if I do this in the other order, if I write them as, in this case, 8x squared plus 12x minus 6x minus 9 equal to 0, I'm still going to get the same factors and thus the same solutions. So if I do GCF of the first pair, in this case I'm going to have 4x, I'm going to be left with 2x plus 3. And when I do the GCF of my second pair, it's going to be a negative 3, and it's going to leave me with 2x plus 3. What's inside parentheses matches 2x plus 3. I'm going to pull it out. It's my GCF. and I'm left then with 4x minus 3 equals 0. So I want to stop here and show you guys that I do have the exact same pair of factors. They're just in the opposite order, right? And remember, multiplication is commutative. A times C is the same as C times A, okay? So it doesn't matter which order I have these binomials listed, they still multiply out to give us the same thing. So the order in which you list those terms when you split the middle term is essentially just going to determine the order which you get for your factors when you get to that factored form of the quadratic equation. Okay, so the order doesn't matter here. All right. So solving by taking square roots. All right. Again, I want to ask myself, do I have a GCF? Here I do. It is 5. Right. So I can factor that 5 out. But even if I didn't factor that 5 out, I could have done this another way. All right. So if I divide both sides by 5, I'm left with x squared minus 9 equal to 0. Right. Because I simply have a squared term and a constant term, and I have no x to the first power term, I'm able to solve by taking square roots. So let me add the 9 to both sides. I'm going to have x squared equals 9. And if I take the square root of both sides, remember, squaring that quantity x guaranteed positivity. So when I take the square root of both sides, right, I need a plus or a minus, because what was in that x could have been positive or it could have been negative. Okay, so anytime I take a square root of both sides, I need a plus or minus, right? Here, square root of 9, we're going to get plus or minus 3. And these are my two solutions. Okay, the other way I could have done that, if I just went straight from 5x squared minus 45, I add the 45 to both sides. I divide both sides by the 5. I get x squared equals 9, right? I do that because before I take a square root, I must isolate that squared term. I don't want the 5 still there. Right, then I take square root of both sides, right, and we end up here. Okay. The other thing I could have done once I factored, or did I just pull up there? Right, once I factored the 5 out, I had 5 times x squared minus 9 equal to 0. I could have also factored this as a difference of squares, x plus 3 times x minus 3. Right, this worked simply because I had perfect square factor of 9 there, right? And I get x equals negative 3 and x equals positive 3. Okay, so I get the same answers. And again, what I'm trying to illustrate to you guys here is there's not always one way, only one way, that's going to work for a particular problem. Okay, there are typically several ways that you could factor and solve each of these individual quadratics. Okay. Next example, I have 4x squared plus 48 equals 0. So again, let's look GCF. I've got a 4 here, so I can factor it out. I have x squared plus 12 equals 0. I can divide both sides by 4. I'm left with x squared plus 12 equals 0. So let's solve by taking square roots. The 12 is not a perfect square, so it's not going to factor as a difference of squares. And in fact, it's a sum. All right, so that's going to present a different problem. Let's see what that is when we go and solve. So when I subtract the 12 over, I have x squared equals negative 12. And when I take square root of both sides, I get x equals plus or minus the square root of negative 12. Okay. I need to think, what perfect square factors do I have for 12? It's going to be 4 and 3. And in fact, I want negative 4 times 3 for those perfect square factors. What we're going to end up with then is x equals plus or minus 2i square root of 3. Again, that negative is going to come out as an imaginary. Square root of 4 is the 2, and I'm left with that square root of 3 behind. All right, so we get plus or minus 2i square roots of 3. One more example with solve by taking square roots. So here I've got the quantity x minus 3 all squared plus 25. Right? What I want you guys to do at this point, like if you have a quantity like this, and there are no variables outside of that quantity, and that quantity is being squared, okay? And here the only thing outside is a coefficient, right? Or a constant, right? I want you to solve this by taking square roots. Yes, I could FOIL that out, right? We would end up with x squared minus 6x plus 9 plus 25 equals 0, or x squared minus 6x plus 34 equals 0. But let me ask this. Can you come up with two numbers that multiply together to give you positive 34 and add to negative 6? No, they don't exist, okay? Or at least not as integers that are going to be easier for us to work with. So right now, this equation over here on the left is already in an easier to work with form. So if I go and try and isolate this squared quantity, right, I'm going to be left with x minus 3 quantity squared equals negative 25. If I take a square root of both sides, I'm going to have x minus 3 equals plus and minus the square root of negative 25. And if I take a square root, or if I simplify that square root on the left, I have x minus 3 equals plus and minus 5i. And now if I finish solving by adding 3, I have x equals 3 plus or minus 5i. Okay? Again, if you have something that's in a form like this where it's already set up to solve by taking square roots, take the easy route and solve by taking square roots, because there's no guarantee that when you FOIL it out that it's going to be factorable. Okay? Which brings me to my next point. Okay? If I have something that were in possibly the form of x squared minus 6x plus 34, I've got a couple of options for how I want to try and solve that. And the first that we're going to cover in this video is completing the square. Okay, so in a quadratic equation, when we can't factor it using integers, we either need to complete the square or we're going to use the quadratic formula. My recommendation in terms of solving is that if a is 1, I would consider using completing the square. Okay, as long as you have easy to work with, nice coefficients. Okay, even if they're fractions. Okay, if your coefficients are reasonable, I would go with completing the square. If you have decimals or if you have horrendous looking numbers in there, you're probably going to want to go to the quadratic formula. Or if the a value is not 1, quadratic formula might be a better option for you. So here's what we're going to do, all right? And even if a isn't 1, we can still do this, and I'm going to address how for solving. Okay? So we're going to rewrite the quadratic equation in the following form. I want you to write it as ax squared plus bx, and then equals, and I want you to move that constant term over to the right. Okay, I want you to move it over to the right. If your a value does not equal 1, I want you to divide all three of your terms by a. Okay, this may introduce some fractions, it may not. If it didn't, you had a GCF. Okay, but if a did not equal 1, you have to divide it, or divide all the terms by that value, because before you do the next step, the coefficient in front of x squared must be 1. Okay, if we're doing this for the purpose of graphing, I have to preserve that a value, but for solving, I can just divide it out. So what I want to do is I want to take that b term, the constant here on x, I want to divide it by 2, and I want to square it. And whatever I get, I'm going to add to both sides. So I'm going to have b over 2 squared. It's being added to both sides. Right? The left-hand side, then, is a perfect square trinomial. Okay? And I'll show you, and hopefully you'll see that when we do an example here in a minute. Okay? So I want to write that as a quantity squared. And if b happened to be negative, right, if this were minus bx, you're going to have the opposite of b over 2 all squared, which is going to give you x minus b over 2 quantity squared. Okay, so if that middle term was negative, your factor when you write it is going to be negative as well. Okay, once you get to this point, then you're going to take a square root of both sides, and then you're going to solve it. Right? Hopefully the c plus whatever b over 2 squared is, hopefully that's nice and easy that you can combine like terms and work your way through it. Sometimes you're going to have some fractions, sometimes you're going to have some radicals. Okay, but again, once you get to this point, now you're set up to solve by taking square roots. So let's do this where we actually have a couple of numbers. Okay, so here I've got x squared minus 3 equals negative 10x. So if I take a look at this, and if I put this into standard form, I'd have x squared plus 10x minus 3 equals 0. And if I ask myself, are there two numbers that multiply to negative 3 that add to positive 10? Obviously, I'm going to say no, they don't exist. So a is 1. Let's try completing the square. So I'm going to take that 3, I'm going to move it over to the right. So I'm going to have x squared plus 10x equals positive 3. Okay, and I'm leaving myself a little bit of room here. All right, and I'm going to put plus and a blank on both sides. Right, so I'm going to take 1/2 of my b term. Right, a is 1, so I don't have to divide anything. So 1/2 of 10 is going to be positive 5. And I'm going to square it. I want to add that to both sides. Now, on the left, if I did write this out, I would have x squared plus 10x plus 25. Two numbers multiplied at 25 and add the 10, it's 5 and 5, right? So what I really want you to do is leave this in that form on the left-hand side as the b over 2 quantity squared. Because whatever that b over 2 is, that's the number that you need for your perfect square trinomial, which we're going to do next here. Okay, so this is going to be quantity x plus 5 all squared, equal to, and on the right, I'm going to have 3 plus 25, or 28. Okay, now I'm going to take a square root of both sides. When I do that, I get x plus 5 equals plus or minus the square root of 28. 28 is perfect square factor. It is 4 times 7. Right, so I'm going to have x plus 5 equals plus and minus 2 square roots of 7. And I subtract that 5 over, I'm going to have x equals negative 5 plus or minus 2 square roots of 7. Okay, I do, for right now, I want you to leave this in this form. This is an exact form for this equation. Okay, yes, I do agree that you can take your calculator and you come up with a decimal approximation. In the quadratic formula, if you have a program in your graphing calculator, is going to give you the decimal, right? But there are a lot of times where I'm looking for the exact answer, and I'll explicitly ask for the exact answer only, right? So this is what I'm looking for as a final solution. Okay, you can use the calculator to verify that you get the same decimal as the approximation here. You know, if you're looking at other means, or if you graph it to see are the intercepts the same as what these decimals tell you. But if I ask for an exact solution, I'm looking for you to leave it specifically in that radical form, because I can't simplify the square root of 7.